In this lesson, we focus on physical sciences. Physics, paper 1, May, June 2024, 150 marks, 3 hours. And we are getting started with the questions. And we actually will discuss first the multiple choice questions. Question 1. Multiple choice questions. Various options are provided as possible answers to the following questions. Each question has only one correct answer. Right, choose the answer and write only the letter A to D next to the question numbers. Write 1.1 to 1.10 in the answer book. E.g., for an example, 1.11 is actually E. Okay, because this guy knows that 1.11 is not there because it's 1.10 is the last one. Right, a book. We're doing question 1.1. A book rests on the table. Which one of the following forces will form an action-reaction pair with the weight of the book? So obviously, we're looking at a situation where we have a table. Right, we have with us a table. The table has legs. On the table is a book. It is resting on the surface of the table, and this is a book. We're asking the question, right? Okay, a book rests on a table. Which on the following forces will form an action-reaction pair with the weight of the book? Is it the force of the earth on the book? Is it the force of the book on the earth? Is it the force of the book on the table? Is it the force of the table on the book? Which one of the following forces will form an action-reaction pair with the weight of the book? The book has a weight. Something is going to form an action-reaction pair there. Okay, that's fine because we're practicing. So obviously what we can see is that this book has a weight W, and now we are then asking the question, which of the following forces will form an action-reaction pair with the weight of the book? Right, with the weight of the book. So if we look at these, obviously, um, okay, and obviously now it thinks that it is the force of the table on the book. Okay, that's interesting. The force of the table on the book. And the action reaction pair with the weight of the book. So obviously we're thinking of these and we're looking at the options given and we are trying to process. Right, we're trying to process. We are trying to process. Right, we are processing. Is it the force of the table on the book that is, which is what obviously you are looking at? Right, is it the force of the book on the table? And is it the force of the earth on the book? Right, so obviously, I mean, we are thinking about this question and we're looking at these very carefully. We are looking at these very carefully. Right, we are looking at these very carefully. Because the question still stands, which of the following forces will form an action-reaction pair with the weight of the book? Right, with the weight of the book. So obviously at this point, what we are actually able to realize that we are looking at the weight of the book. The weight of the book describes a force between the book and the earth. So this is Newton's third law. The force between the book and the earth is called the weight of the book. And obviously this is the force of attraction. This is the force of attraction. And so if we're then saying that the weight of the book is actually the force of attraction between the book and the earth. Okay, I'm glad that you're thinking about it. So this weight, it's the force of attraction. It is the magnitude by which the earth pulls everything to itself. So now this one, the weight, it's a force between the book and earth. Book and earth. Okay, this is the force between the book and the earth. Because we speak about the force, which has two objects, right? M1, M2 over R squared, the buildings we were talking about earlier on WhatsApp. And so obviously now the truth is that we are looking at these, we are looking at two things. We're looking at the book and we're looking at the earth. And we're looking at the fact that the force here is the weight, Fg. So now, and this is actually now the weight of the book. The weight of the book is actually a downward force. It's a downward force. And now we need to look at an action reaction pair. So we need to look for an upward force. Upward force. So this weight is downwards. And it is towards the earth. And therefore, it is now, if you look at the option A, the force of the earth on the book, it's the weight. So this one still describes the weight. But the force of the book on the earth, it is the one, because the book is also attracting the earth upwards. And the table does not matter. So the truth is we must remove the table out of the equation. Because when we're speaking about the weight, we're speaking about the object that is experiencing the weight. So now at this point, we shall surely say, in this particular question, we want to look at the upward force. What is pulling the earth? What is actually an upward force here? What is the upward force? Because the downward force is the weight, which is the force of the earth on the book. And so if now we want to look at an upward force, it will be the force of the book on the earth, because the book is also attracting the earth. The book is also attracting the earth by a force of the same magnitude but opposite direction. So obviously the correct answer will be the force of the book on the earth. It's the one that is an action reaction pair. It's the one that is an action reaction pair. Because A is close, but it's the force of the earth on the book. The force of the earth on the book is the weight still. So this one is not action reaction pair. But the book now is also pulling the earth up. It's pulling the earth up, and therefore there is an action reaction pair by Newton's third law. By Newton's third law of motion. We look at the next question. A person is standing on a bathroom scale. Here's the bathroom scale. And this guy is standing here. Standing there. Right, a person is standing on a bathroom scale. And now when this happens, a bathroom scale. Person is standing on a bathroom scale. Right, in a moving lift. Okay, but obviously they're telling us the lift is moving. The next question we must ask ourselves, is it moving upwards, downwards, sideways? What direction is the lift moving? Because it is moving, because that for us is very important to determine the forces acting on the person, etc., the bathroom scale. Which are the following motions of the lift will result in the smallest reading on the scale? Okay, we want the smallest reading on the scale, which are the following motions of the lift. That's the thing. So to make sure that this person has the smallest reading on the scale, maybe they are too fat, but they want the smallest reading to make their friend happy that, you know what, this guy is not so fat, he's not so heavy, you are heavy. So, see, that there can be that kind of an argument. So the lift accelerates upwards. If the lift accelerates upwards, will the scale on the lift be on the scale on the bathroom scale be more? Will the reading be more, or the reading be less weight? Okay, or less mass. B. So if it accelerates upwards, if now the lift accelerates downwards, will the bathroom scale read less? If the lift moves upwards, but at a constant velocity, or it moves downwards, but at a constant velocity. Oh, okay. But obviously, see, if it moves at a constant velocity, it means that the downward and upward forces are actually equal in magnitude but opposite in direction. So now if it accelerates downwards, that will be downwards. Because if it accelerates upwards, then there are a couple of things that will happen there. So here's the bathroom scale. And if it accelerates upwards, then there will be the force by the lift, right? And so there will be the force by the lift, because the lift is accelerating upwards. So if then it accelerates downwards, then it means, therefore, you're going to have a situation where the force by the lift is obviously it's downwards. It's a downward force. And now, as a consequence, then it actually somehow minimizes the compression between the the bathroom scale and the feet of this person. So that compression is reduced by the downward motion. And when that happens, therefore, it means that it is only the downward that will do the job. It is only the downward that will do the job. Because if it's downward, then if it's upwards, then it is pushing the bathroom scale against the shoes of this person, against the feet of this person, increasing the force of contact, and now increasing the magnitude of the force of contact, and therefore increasing the reading on the bathroom scale. But if this lift is to go down, then the opposite happens. Because if the lift goes down, then it means that there is a decrease in actually the force of compression between the bathroom scale and the feet of this person, and as a consequence, therefore, that would give the smallest reading of on the scale. That will give the smallest reading on the scale. That will give the smallest reading on the scale. Right. Okay, let's look at the next question. The velocity versus time sketch graph below represents the motion of all, or rather the motion of the ball, which was in free fall. Okay, this is in free fall. Here comes the ball, and the ball is in free fall, and the only force acting on it is gravity. Right, to which, because it's in free fall. It's in free fall. The ball struck the ground after 3t seconds. It struck the ground after 3t seconds. Okay, let us read a couple of the things here. Which one of the following statements is correct? Which one of the following statements is correct? Which one of the following statements is correct? Right, which one of the following statements is correct? Okay, so let us check this one out. Let us check this one out. Which one of the following statements is correct? The ball was, okay, yeah, the ball was dropped from a height above the ground. Okay, because now if the ball struck the ground after 3t seconds. So if we analyze this graph together and we say, okay, now what thinks it's C. The ball was thrown vertically upwards from the ground. In C, thrown vertically upwards from a height above the ground. Thrown vertically upwards from a height above the ground. Thrown vertically downwards from a height above the ground. Okay, what exactly happened? The velocity became zero here. So Noah thinks it was thrown vertically upwards. So it had an initial velocity, but its velocity became zero. It was thrown vertically upwards from a height above the ground. Then you can see, therefore, that its velocity increased to some VF, but the time became a bit longer. The time became a bit longer. So if the time became a bit longer, then what must have happened? What must have happened? Yeah, now it's on point. Now it's on point. It was thrown vertically upwards from a height above the ground. Because the time here, so it moved like this, and then its velocity became zero at maximum height. And then, but you can see that there was a longer time there. There was like up to time 2t, but it was continuing again up to like time 3t, so this was like 2t. If it went up at time t and then came down at time t, at time 2t there. So obviously then it was thrown vertically upwards from a height above the ground. That is the truth. That is the truth, because we are able to see that right now it is actually 3t seconds. So it has taken much longer after the maximum height of zero velocity, still traveling to reach a final velocity. So it reached a final velocity at a time, after a time of twice t, because the 3t minus t is like twice t. It took like double the time, because it was like time t seconds here, time 2t seconds here. So it took double the time to actually reach its maximum, its final velocity. So yeah, it makes sense. Okay, we're good. We're good. Yeah. So Noah's on point. Noah is on point. Next question, 1.4. The vector diagram below shows the initial momentum P1, the final momentum P2, and the change in momentum, change in P, for a car that moved on a straight horizontal road. See, there's a initial momentum P1, final momentum P2, and the change in momentum delta P. Right, for a car that moved on a straight horizontal road, this was like a straight horizontal road. Which one of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road? Just check the graphs here. Okay, if we get graph 1, graph A, the vertical axis is the momentum axis. You need to analyze it very thoroughly, obviously, because multiple choice are tricky. They are tricky, right? So the momentum is the vertical axis, and the horizontal axis is our time axis, right? So we are able to see clearly a couple of things here. That, for example, if the vertical axis is the momentum axis, right? The momentum was constant. It actually decreased, and then it became constant again. The momentum was constant. Okay, now thing to see. The momentum was constant. It then increased and then became constant again. The momentum was constant. It then decreased and then it became constant again. The momentum was constant. It then increased and then became constant again. But here it actually such that it decreased, became zero, and then it was momentum in the negative. Because if the change in momentum is in the opposite direction, what then would be the case? Okay, now what things did it say? Let's analyze that. Right, let's analyze that together. Let's analyze that together. Okay, because if you're then saying the Venn diagram below shows the initial momentum P1 and the final momentum P2 and the change in momentum for a car that moved on a straight road. Okay, what should we pick from these? Momentum P1 is big. It's big because the magnitude is it's big. The magnitude is big. But momentum P2 is small. It has a smaller magnitude. Has a smaller magnitude. And this one has a bigger magnitude. So, so you have the magnitude. Right, we have the magnitude. So momentum P1 is big. The size is big. And momentum P2 has a smaller size. And suddenly you can see that the change in momentum is actually momentum in the opposite direction. But we know that the change in momentum is what? Is final momentum minus initial momentum. So at this point, this one is so big. So because it's so big, let's give it some magnitude, yeah? And then we can call it, suppose it is 5. In this one, it is 2. And then now you can say the final momentum is going to be 2, the initial momentum is going to be 5, and therefore the difference is minus 3. Obviously, it's kilogram meters per second. This is the SI unit of the change in momentum. So now at this point, because it is in the opposite direction, you can see it is in the direction of momentum P1. So now if then we get back to answer these questions to say which one of the following sketch graphs correctly shows the momentum of the car for the time the car moved on the road. Initially, when the time was 0, we had constant momentum. And then the momentum became negative. The momentum was in the opposite direction, so it became negative. So it therefore makes sense to then obviously think of what happened in that case. It makes sense to think of what happened in that case. So if these were like in that direction, both of them, and then suddenly the change is in the opposite direction, it actually means the change was actually a negative change. But obviously, if we look at the two things here, you can see that it makes sense to say that the initial momentum was positive, the final momentum was also they were in the same direction. So these were actually both positive because they were in the same direction. Or they could both be negative, then both below. If you choose the initial direction as negative, of course. And then it means that at this point, the initial momentum was positive, but then suddenly this momentum is of smaller magnitude. So this momentum became smaller. the momentum was big. It was big because it's long, it's vectors. It was big because it's long, and then it became smaller. Obviously, this won't be the case because it means the final momentum became bigger. So here, obviously, it means that the other momentum became negative. Not the case. Negative means in the opposite direction, but they are in the same direction, both to the right. So obviously, if you look at D, you're able to see the initial momentum, negative initial momentum. So now the other momentum, the final momentum became like positive, so it became like in the opposite, the final momentum. So these are out, and that is out. The only correct option is that one, because the initial momentum was that, and then the momentum reduced. So which means that in 1.4, the correct option will have to be option A. Of course, the change was negative, but this is like momentum P1 and momentum P2, which were both in the same direction. So if these were in the same direction, therefore, in terms of vectors, then they must have the same sign. They must both be positive. Or, of course, they could both be negative, but yeah, both positive. Anyway, just something for you to know there. Something for you to note there. Something for you to note there. Right. Now yours, something to note. Right. Right. All right. Let's move to the next point. Next question. A stone of mass m is dropped from a height h above the ground. Here is a stone of mass m. It is dropped from a height h above the ground. Ignore the effects. So now somebody's dropping a stone. Right? Somebody's dropping a stone. And what we're then seeing, right? What we're then seeing is that this stone is dropped from the center of the stone to the ground. The height is h. The height is h. Okay. A stone m is dropped from a height h above the ground. Okay, ignore the effect of air friction. Which one of the following combinations in the table below correctly represents the kinetic energy and total mechanical energy of the stone at the instant? At the instant the stone has fallen through a distance of 1/4 height. Which of the following combinations in the, because it is dropped from a height of this. If it is dropped from a height of this, it means that the initial velocity is 0 meters per second of the stone. Okay, good. Now it thinks it is B. That's fine. Which one of the following combinations in the table below carefully represents the kinetic energy and the total mechanical energy of the stone at the instant the stone has fallen through a distance of 1/4 of the height? Okay, let's check. The kinetic energy is this, like 3/4, and the total mechanical energy is 1/4. The kinetic energy here is 1/4 mgh, and the total mechanical energy is 3/4. C, 3/4 of mgh, mgh, and 1/4 of mgh, mgh. So now we are having a perfect chance. We are asking the question, which one of the following combinations in the table below correctly represents the kinetic energy and the total mechanical energy of the stone at the instant it has fallen 1/4 of the height? Okay, if it has fallen only 1/4 of the height, it would mean a couple of things, but it would mean, therefore, at this point it has fallen that, but the total mechanical energy is actually the same as EK plus EP at any given point, which is mgh. So okay, what is the mass? So now you'd be able to see that at this pointer, you would have the following that we have. If it falls this much, you would actually understand that the total mechanical energy at this point would be, right? So you would understand that it has lost mgh. So the total height is in two parts. So you'd have mg, there's going to be 1/4 of the height, there's going to be 3/4 of the height. Okay, because that is the total height. So if ever it happens now with the total mechanical energy, because the mechanical energy, which is the total energy it possesses at this point, the total mechanical energy is sort of mgh at the top, because that is where we have the total height. And then now at this point, if ever it has got to this point, then you'd be like, okay, there's energy conversion. So when it falls this much, it means that from the mechanical energy, there's going to be a loss. Okay. Right. We're actually then saying the couple of things that happen, obviously, in this case. But it is the fact that at the highest point, it possesses mechanical energy. What is the mechanical energy at the highest point? The total energy of the system would be the total energy that it has, and that is the potential energy. Only potential energy at the moment that just before it is dropped, it is mgh of potential energy. So the mechanical energy at the top, at any given, the total mechanical energy can only be can be determined precisely as mgh. Okay. Now, then a time comes, so it is going to reach a point where it has kinetic energy, then, but it has potential energy at this point. If it has fallen 1/4 of these, it means that we have 3/4, okay, because 3/4 plus 1/4 is like a full. So, like one whole, so it's going to be this, but what is the height? The height, which is 3/4. Okay, so it's gonna be 3/4. Okay, potential energy is always the energy possessed by an object by virtue of its height. So it means that now we want to get the kinetic energy, so we can get the kinetic energy because the potential energy, when it has fallen 1/4, then it has fallen 1/4. But what is its height? Because then we can determine the potential energy, so it's 3/4. And then now, if you then say 1 minus 3/4, so you'll be able to see that the kinetic energy, or out of this mechanical energy equation, it's gonna be 1h minus 3 of this. It's gonna be actually 1/4 of mgh. Yeah. Okay. Let's reason these together now again. Okay, in the exam, they ask you about potential energy. Or all potential energy is like the energy possessed by an object by virtue of its height. So if we want to get the total energy at the highest point, it is mgh. That is the total mechanical energy the object has. Okay. Yeah. Good. Let us draw a clearer diagram. Let us draw a clearer diagram. Okay, two things are happening here. The stone is actually first not moving, and then it is dropped, and because it is dropped now, it is allowed to move. Okay, here comes the stone. And the stone has a height h above the ground. We have the height h above the ground. Okay, here comes the stone. It falls down. It falls down a quarter of h. It falls down a quarter of h. The question is, what is its potential energy? Its potential energy is going to be the height that is remaining. How do you know the height that is remaining? Okay, you can take h and then minus the fallen height, and then you would have 3/3. So it'll be like, okay, the remaining height is 3/4. The remaining height is what? Is 3/4. The remaining height is what? Is 3/4. The remaining height is what? Is 3/4. The remaining height is 3/4 of h. Okay. So what is the potential energy? The potential energy is mg height. The height that is remaining after it has fallen 1/4, after it has fallen 1/4 is 3/4. But the total mechanical energy at the highest point is mgh at the full height, which is mgh. So now we solve for kinetic energy from this equation because we want to get the kinetic energy. So to get the kinetic energy, then you therefore say, what is kinetic energy? So kinetic energy from this equation, because mechanical energy is a sum of potential in what? In kinetic. Okay. Then you then say kinetic energy is mgh minus 3/4 mgh. Okay, then you subtract these, then you have 1/4 mgh. Which is 1/4 mgh. So which means, therefore, the kinetic energy is what? Is 1/4 mgh. Okay? So the kinetic energy is going to be 1/4 mgh. So if you look at 1.5, the kinetic energy is going to be 1/4 mgh, but yeah, it appears in two places, so you must choose between B and what? Between B and D. But now you must also look at the potential energy, the total mechanical energy. So obviously, what is the total mechanical energy? That is the thing. So the total mechanical energy, obviously, at this point, does not change. The total energy is what we had before. It is the same. It's just that there's energy conversion from potential to kinetic by virtue of the motion. So in the end, then you have mgh, and the correct answer becomes, but the mechanical energy becomes mgh, and the kinetic energy now becomes just 1/4 of mgh. Any question? Think about it. Any question? Think about it. Yep. Okay. Okay, you think you lost. Okay, let's think about it. Let's talk about it again. Because see, they brought the trick. The trick in this question is that kinetic energy is called mgh, but you see, kinetic energy should be half mv squared. So, what is mechanical energy? Mechanical energy is EK plus EP. Okay, always. So now, what is mechanical energy? The mechanical energy is the total energy at the highest point before the energy conversions took place. So it is going to be mgh. It's going to be mgh. It's going to be mgh. Okay. Then you have the kinetic energy. The kinetic energy, which is EK, and then the potential energy after this object, the stone, after the stone has fallen 1/4, after the stone has fallen 1/4 of the height, then what is the potential energy? It's mg, the height. What is the height? It's 3/4 of the height that is remaining. Okay, mechanical energy is mgh at the top, because it's not moving. There's only one form of energy there at the top. It's only what? It's only potential. But when it reaches the middle here, there's going to be both kinetic and what? And potential. So we have mg, the height is 3/4 h. So that we have mgh minus mg 3/4 h, which is mgh minus 3/4 of h. So what is mgh minus 3/4 of h? Which is 1/4 of mgh. 1/4 of mgh. 1/4 of mgh. 1/4 of mgh. So this 1/4 of mgh is the kinetic energy. So we just made kinetic energy the subject of the equation here, because the potential energy at this point is going to be subject to the height. The height is 3/4 of h, but the total mechanical energy at the full height is mgh. Now, making kinetic energy the subject of this equation, it becomes mgh minus 3/4 of this, and therefore we have mgh minus 3/4 of mgh, which is 1/4 of mgh. So the kinetic energy is 1/4 of mgh. But what is the total mechanical energy? It's the potential energy at the highest point, which is mgh. So the total mechanical energy is mgh, whether it has fallen or not. The total mechanical energy is everything we have, which is mgh. I hope you understand now. Right. I trust you and you sort of understand. Too easy. I trust you sort of understand, because you see, multiple choice can be tricky. They can be tricky, but you need to have your way of getting around the multiple choice, because they really can be tricky. Very, very tricky. Very, very tricky. Okay, let's look at the next question. I'm sure you're going to be fine. The spectrum of helium emitted from a star. The spectrum of helium emitted from a star moving away from Earth is compared to the spectrum of helium found on Earth. The spectrum of helium emitted from a star moving away from Earth. Okay, so we have Earth, and then we have a star. This star is moving away from Earth. This star is moving away from Earth. So we're comparing the spectrum of helium emitted from a star moving away from Earth is compared to the spectrum of helium found on Earth. The spectrum of helium compared to the spectrum of helium found on Earth. Okay, which of the following statements is correct? The observed spectral lines from the moving star will have a what? The observed spectral lines moving, okay, yeah, the observed spectral lines from the moving star will have a what? Lower frequency and a longer wavelength? Lower frequency and a shorter wavelength? Higher frequency and a shorter wavelength? Higher frequency and a longer wavelength. Okay, they're trying to confuse you here. They are trying to confuse you here. Okay. So the one that is moving, the spectrum emitted from a star moving away from the Earth, a star that is moving away from the Earth, because it is moving what? Because it is moving away, we said it is red shifted. Red shifted is like a car that is having the brake lights. Here's a car, a sedan. Okay, that thinking you're thinking the very well done. A is the correct one because it is red shifted. So red shifted. Now, if you look at the red shifted, when we speak about the red shift, then they will have lower frequency and a longer wavelength. Lower frequency and longer wavelength for the red shift. For the red shift. In view of the spectrum of this, and now you're looking at what you call the Roig Roig-Biv. So at this point, this side, you have lower frequency and longer wavelength at the red, orange, yellow, green, blue, indigo, violet. Right, and obviously, you see, when you are here at the red part of the spectrum, you have lower frequency and longer wavelength. Lower frequency and longer wavelength. But obviously, you note that whenever you have lower frequency and longer wavelength, and vice versa, right, and vice versa. So whenever the wavelength is longer, then the frequency is lower. Then the frequency is lower. Then the frequency is lower. Okay, good. So the correct answer is A. The rest are out. Next question. The magnitudes of electric fields generated by different point charges are measured at a fixed point for each measurement. The distance between this fixed point and the charges are the same, which on the following sketch graphs correctly shows the relationship between the magnitude of the electric field E and the magnitude of the charge. Okay? The magnitudes of electric fields generated by different point charges are measured at a fixed point. The magnitude of electric fields generated by different point charges are measured at a fixed point. Okay? We continue. We continue. The magnitude of the electric fields generated by different point charges are measured at a fixed point. Your magnitude of electric fields generated by different point charges are measured at a fixed point. Okay. measurement, the distance between these fixed points and the charges are the same. For each measurement, the distance between these fixed points and the charges are the same. Which one of the following sketch graphs correctly shows the relationship between the magnitude of the electric field and the magnitude of the charge? Let's look at this. Right, F equals QE. Right. E equals F over Q. And then the electric field strength, because we're speaking about the electric field, is measured therefore in newtons per coulomb. So now, if you want to look at the relationship between E and that in the 1.7, you need to think of these very carefully, because the magnitude of electric fields generated by, okay, that's interesting. That's very interesting. So the magnitude of electric fields generated by different point charges are measured at a fixed point. For each measurement, the distance between these fixed points and the charges are the same. The magnitudes of the electric fields generated by different point charges are measured at a fixed point. We're measuring the magnitudes of electric fields generated by different point charges are measured at a fixed point. There's a point charge, there's a point charge, there's a point charge. Okay, and these point charges, the magnitudes of the different electric fields generated by different point charges are measured at a fixed point. Right, so they somehow have fixed point, and we're measuring, right, at a fixed point. For each measurement, the distance between the fixed point and the charges are the same. Yeah, the distance, okay. Yes, for each measurement, the distance between the point charges and that are the same. So yeah, anyhow, you actually obviously, if you have the fixed point and the distance is the same, so we can have same distance, but there's a fixed point, yeah, so you possibly place them there, but it's the same distance. So which one of the following graphs correctly shows the relationship between the magnitude of the electric field and the charge Q? Right, so obviously you really are spot on that the correct option here in 1.7 is going to be exactly option A. Because you know that E equals KQ over R squared. Right, and by dint of this, you're able to actually observe the actual direct relationship in view of the distance. That the distance between them is fixed, and therefore you're able to see a direct relationship there. So option A is actually the very, very correct one. It's a very, very correct one. The very, very correct one. So very well done. Move on to the next question. The diagram below represents a circuit in which all the external resistors have the same resistance. So this one, same resistance, same resistance, same resistance. Same resistance, same resistance, same resistance, same resistance. Okay. Right. So you continue. Right, we continue. We continue. Okay, yeah. Which one of the following ammeters in the circuit will have the lowest reading? Lowest reading. So the ammeter with the lowest reading will be subject to the lowest current. Would it be this one? This one is connected to a battery, so we expect it to have sort of a lot. And then this one, there's sort of some current reduction there. And then now there's this one. So when the current gets to this point, it's going to split. Some of it is going to go there, go there. So this one is going to pass through these resistors, reduced current, reduced current, reduced current, and gets to this point. So now, right. Right, we continue. Yeah. Of course, yes. It is obviously from the positive terminal. So obviously this point, this is the positive terminal, the longest one. So we expect the current to go in that direction. So obviously the way, what then would happen is there's going to be a split of the current. So it's going to come like this. Some of it will go there, some of it will go there. So there's going to be a split. Okay, yeah, it's going to be split. Let's analyze this. Let's analyze this. 1.8. Let's analyze this. 1.8. Let's analyze this. 1.8. Okay, yeah. Anyhow, that's what we're going to have. So now we're looking at 1.8. Which one will have the least reading? They said now if it comes like this, there's going to be a lot of the current, but it's going to be a current reduction. Okay, I'm glad. So there's going to be, some of it is going to split it going there. So now if it comes here, then it's going to be reduction. But if it gets to this point, there's going to be a split, but even further reduction, etc. And so it is correct to then say that at this point, it's going to be in 1.8, it's going to be C. It's going to be C exactly. It's going to be C exactly. So obviously we agree therefore that at 1.8, This is going to be C exactly. So in A3, then you're going to have the lowest possible reading. You're going to have the lowest possible reading. Right, you're going to have the lowest possible reading. In particular, that will be by dint of these two resistors that are packed adjacent to these A3. They would have massive power reduction effect. Massive power reduction effect. Massive power reduction effect. One 1.9. A simplified diagram. Okay, good. Right, a simplified diagram of an electrical machine is shown below. A simplified diagram of an electrical machine is shown below, where you have the south pole, the north pole, and you have a power source. And there, obviously, see the presence of the power source means that obviously what we're dealing with here is actually a motor. A motor, and it's not a generator. Not a generator. Okay, so what type of machine is it? Okay, yeah, that's interesting. 1.9. Right. So obviously we are able to see that as you have correctly said, it is a direct current motor. It is a direct current motor. So obviously you really are on point. It is certainly a direct current motor with the power source there. It is direct current motor with the power source there. As we have indicated that it is not a generator. A generator does not go with batteries. So it's not a generator. It's not a generator. It's not a generator. It's not a generator. So we have 1.10. Which one of the following combinations? Okay, good. Right, which one of the following combinations is correct for a line absorption spectrum in terms of the energy transition of the atoms and the appearance of the narrow lines in the spectrum? Which one of the following combinations is correct for a line absorption spectrum? So we're speaking about a line absorption spectrum in terms of the energy transitions of the atoms and the appearance of the narrow lines in the spectrum. Let's look at 1.10. Let's look at 1.10. Let's look at 1.10. The energy transition of the atoms. The energy transition of the atoms. Okay. The energy transition of the atoms. The energy transition of the atoms. Right, so obviously you need to look at this. The energy transition of the atoms, is it higher to lower energy state? lower to high energy state, lower to, okay, let me check what Neo is saying. Okay, Neo thinks that it is A, right? Okay, I'm seeing other things now. I'm seeing other things that just moved. Right, so obviously Neo thinks that it is A, right? Neo thinks that it is A. Okay, yeah, maybe not quite yet. Not quite yet. Never mind. Right, so the energy transition of the atoms will be higher to lower energy state, lower to higher energy state, lower to higher energy state, higher to lower energy state. Appearance of the narrow lines in the spectrum would be dark lines, colored lines, dark lines, colored lines. Okay, just dark colored, that kind of alternation. So obviously at this point, what then we can say is in 1.10, because we're saying which one of the following? Which one of the following combinations is correct? Is correct for a line absorption spectrum in terms of the energy transitions of the atoms and the appearance of the narrow lines in the spectrum. Right. Which one of the following combinations is correct for a line spectrum in terms of the energy transitions of the atoms? So the energy transitions of the atoms and the appearance of the narrow lines in the spectrum. Right. 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 And when it comes to the energy transitions of the atoms, you know very well that lower to higher energy state, right? We know very well that lower to higher energy state, the appearance of the narrow lines in the spectrum become dark. Lower to higher energy state, it means therefore that the appearance of the narrow lines are dark. So it is option C. Is option C. It is option C. It is option C. It is exactly option C. It's exactly option C. Okay, lower to high energy state means the appearance of the narrow lines in the spectrum will be the dark line. Dark lines. Dark lines. Lower to higher energy state. Let's look at the next question. Okay, remember this, we spent a lot of time on this one. We did this one. And then we did this one. We just had to do this one. Do this one. No, we did not do this one. Let us do question 4 on momentum. Question 4 on momentum. Two trolleys A and B of mass 3.2 kilograms and 2.6 kilograms respectively are held at rest on a straight horizontal frictionless track. Okay, and these are held at rest, right? And it is frictionless, right? With a compressed spring between them, as shown in the diagram below. Before the spring is released, this is the setup. The track is there. The compressed spring is there. 3.2 kilograms, 3.6 kilograms. Before the spring is released. Before the spring is released. After the trolleys are released, because it was compressed, the spring itself was compressed, the spring extends to its natural length and then falls onto the track. Trolley A now moves with a constant velocity of 0.4 meters per second to the left, while trolley B moves with a constant unknown velocity to the right. Trolley B reaches the end of the track after 1.3 seconds. Trolley B reaches the end of the track after 1.3 seconds. State the principle of conservation of linear momentum in words. State the principle of conservation of linear momentum in words. State the principle of conservation of linear momentum in words. Right, and we can state as follows. We can state the principle as follows and say in an isolated system, the total linear the total linear momentum is conserved. Is conserved. Is conserved. In an isolated system, right, the total linear momentum is conserved. That is the principle. Calculate the distance traveled by trolley B in 1.3 seconds for 5 marks. Let me give you a chance. Calculate the distance traveled by trolley B in 1.3 seconds. Okay, let me give you that one for like some 3 minutes. Give you that one for some 3 minutes. Let me give you this one for some 3 minutes. Let's see what you can do. Let's see what you can do. Let us see what you can do. Right, let us see what you can do. 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 Okay, let us know when you're done, please. Okay, good. We shall do work energy. Okay, let's do work energy, right? Okay, let's do work energy. That's fine. Okay, you suggest us to work energy. Let's do work energy. There's lots of marks, maybe. Okay. Okay, good. That's fine. A crate of mass 18 kilograms initially at rest slides down a frictionless slope. It slides down a frictionless slope from point A to point B. The crate then moves along a rough horizontal surface from point B towards point C. Point A is 3 meters above the horizontal surface. Okay. Okay. Okay, can we finish the momentum, right? Okay, let's finish the momentum. Okay, I thought maybe you thought we need to move because yeah, I was asking you there to just do um the distance traveled by the trolley in 1.3 seconds. The distance traveled by the trolley in 1.3 seconds. Please let us know when you're done. Right, please let us know when you're done. 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 So how do you find the distance? Right, how do you find the distance? Right, so let us know when you're done. Yep. All right, that's fine. It's just about 1 meter. It's okay. So Nemo thinks that the distance traveled by the trolley is actually just 1 meter. The distance traveled by trolley B is just 1 meter. That is what Neo suggests. But yeah, let's just look at it together. But first and foremost, because we know that this is a momentum situation. So now the couple of things that we need to look at, obviously, here. Because trolley A now moves with a constant velocity of 4 meters per second to the left, while trolley B moves with a constant unknown velocity to the right. right? Trolley B reaches the end of the track. So you see, when it reaches the end of the track, it means a couple of things, right? And so it means that what we're going to have here is that we have the summation. We have the summation of initial momentum and the summation of final momentum, which means MAVA plus MBVB is MAVA plus MBVB. Right, remember that these were held stationary together and initially, so we're going to have initial, and then we're going to have final. Initially, these things were addressed, all of them, so there was no motion. And then now, after this, then we have the 3.2. But need to choose direction. So now trolley B reaches the end of the track in that amount of time. Right, so if you look at trolley A, if you choose the motion to this side as positive, so choose left as positive, so that this one is going to be 3,2 of mass of A, 0.4 meters per second. The mass of B is 2.6. And then we have the final velocity of B. So which means that the final velocity of B is minus 3.2, 0.4 divided by 2.6. And this is minus 0.49 meters per second. So this would be the final velocity of B, but obviously because it is negative, it's indicative of the fact that it is 0.49 meters per second to the right. Okay. So if this became the velocity of B, then you can then be rest assured that it reached then the end of the track. But what we then know is therefore that B is delta X delta T, which is 0.49 delta X delta T, which is 1.3. 0.49 times 1.3. So now we're going to take 0.49 times 1.3, 0.67. So it's 0.637, 0.64, 0.64 meters, 0.64 meters, meaning that what you're going to have here, it's going to be exactly a 0.64 meters of displacement. So that is it. So in other words, in the 1.3 seconds, it's going to travel that much. It's going to travel that much. Right. So think about it. Right, so think about it. Okay, good. And then now let's try the next question. The average force exerted by the extended spring on each trolley while they were in contact with the spring was a force of 4.2 newtons. So the average force, which became the net force, was 4.2 newtons negative. The average force exerted by the extended spring on each trolley while they were in contact was this. If you choose to the right, it's positive. Calculate the time it took the spring to extend to its natural length. So we're going to use impulse. So impulse would be F net delta T is equal to delta P. Okay, good. Why is it negative? Right, why is it negative? Because we're told that the average force exerted by the extended spring on each trolley, while they were in contact with the spring was 4.2 newtons. But you need to remember that if you have the trolley here, this spring is going to exert a force in that direction, it's going to exert a force in that direction. And obviously the kind of force we have is sort of the net force. Because now we understand that if we are actually to choose to the right is positive, what then you have, for instance, on a given, on this one, it would be to the left. On trolley A, the force will be to the left, making it negative. Anyway, it's a force that sort of resists and pushes the trolleys away from each other. And in that sense, therefore, is a tendency of being negative. Okay, but yeah, I mean, if we choose to the right as positive, then this is going to be a negative force. That is going to be exactly a negative force. So F net. When I use impulse, impulse says that F net delta T is change in momentum, which is F net. Delta T is change in momentum, which is M. V final, V initial. F net is minus 4.2 newtons. Delta T, if we consider the 3.2, so it's going to be a negative if you consider the 3.2, because pushing the 3.2 to the left, obviously we chose to the right is positive. So that's why it will be negative for the trolley A. So that you have 3.2 meters. The final velocity became 0.4. The final velocity of trolley A became what? 0.4 meters per second. Minus. But obviously we know very well that the initial velocity of trolley A was 0 because there was no motion. We're looking at trolley A when the spring was pushing trolley A, bossing trolley A to the left. And bossing trolley A and pushing trolley A to the left led to a negative net force. Because it became a force to the left that moved the trolley A to the left. We're interested in finding the change in time, which is 3.2 multiplied by minus 0.4 divided by minus 4.2, and the correct answer is what? The correct answer is what? which is 3.2 times 0.4. Yeah, I'm going to check the charts. Divided by 4.2. And we're getting actually plus 3.04. 0.3 seconds. So getting the time to actually become 0.3 seconds. Right, we have the time that is 0.3 seconds. Okay. Yes, you focus on one trolley only. You focus on one trolley only. Because you're looking at the change in momentum of one trolley only. And you're looking for the time it took the spring to extend to its original length or to its natural length. To its natural length. Right. To continue. Right. So obviously now we are looking at the change in momentum. When we're dealing with impulse, we look at an object. When dealing with impulse, we look at an object. Because they are not coupled to one entity, one object. Right. So in the end, then we're interested in finding the what? The time it took, and therefore the time it took is 0.3 seconds. The time it took because it had an initial velocity of 0 when there was no motion. So there was initial velocity of 0, final velocity of minus 0.4. Right, so yeah, so that's what we have. Okay, good, we continue. The average force exerted by the extended spring on each trolley while they were in contact with the spring was 4.2 newtons. While they were in contact, it was 4.2 newtons. Trolley B is now replaced by trolley C, which has a larger mass. Okay, because there were two trolleys A and B, but now trolley B is replaced by trolley C, which has a larger mass, or is heavier. The same compressed spring is now placed between trolleys A and C. Now we are using A and C. B is out of the picture. The trolleys are then released. The average force exerted by the extended spring on the trolleys remains 4.2. It remains 4.2 despite the fact that trolley C is heavier, is larger, for the same period of time as calculated in 4.3. How does the magnitude of the trolley, how does the magnitude of the velocity of trolley C compare to the magnitude of the velocity of trolley B? How does the magnitude of the velocity of trolley C compare to the magnitude of the velocity of trolley B? Okay, how does the magnitude of trolley C compare? How does the magnitude of the velocity of trolley C compare to the magnitude of the velocity of trolley B after the spring has fallen on the track? Right, only greater than. Now, if we put a bigger and a larger, a trolley which has a larger mass, how does the magnitude of the velocity will now C be too fast or too slow? Because we want just the magnitude of the velocity of trolley C. Because we're at trolley A and then we're at B. Now we have A and then, okay, I'm going to check your charts and then see, but C is big. This B was small. Which one is going to be faster here? Which one is going to be slower? That's the thing, right? Only greater than. How does the magnitude of the velocity? Okay, it makes sense. Obviously, Neo thinks that it's going to be less than. Well done. It's going to be less than because it's too big. It's going to be less than. Right, it's going to be less than. Let us explain the answer. Let us explain the answer. Let us explain the answer. The final momentum or the change in momentum the change in momentum the change in momentum or impulse remains constant. Remains constant. The final momentum or the change in momentum or impulse remains constant because of this, the fact that this remains the same. So if mass or inertia increases, velocity decreases. Velocity decreases or velocity inversely proportional to mass. The final momentum, change in momentum, impulse remains constant. If mass or inertia increases, velocity decreases, and velocity inversely proportional to mass. Inversely proportional to mass. Velocity inversely proportional to mass. Right. Final momentum, change in momentum, impulse remains constant. Mass or inertia increases, velocity decreases, velocity inversely proportional to mass. In the sense that change in momentum is m delta v. And so now when we use delta divided by m, velocity inversely proportional to mass. Velocity inversely proportional to mass because it's in the bottom. It's at the bottom, so velocity is inversely proportional to mass. Let's look at the next question. Right, a crate of mass 18 kilograms. Right, initially at rest, slides down a frictionless slope of from point A to point B, frictionless, so there's no friction. The crate then moves along a rough horizontal surface from point B towards point C. Here. Point A is 3 meters above the horizontal surface. See the diagram below. See the diagram below. State the principle of conservation of mechanical energy. State the principle of conservation of mechanical energy. Here is the principle, and we say the total mechanical energy. Right. The total mechanical energy in an isolated system is conserved. The total mechanical energy in an isolated system is conserved. Or if you want to say it's conserved, you say it remains constant. So the total mechanical energy in an isolated system is conserved or remains constant. The total mechanical energy in an isolated system is conserved. The total mechanical energy in an isolated system is conserved. The total mechanical energy in an isolated system is conserved or remains constant. So using energy principles only, calculate the speed of the crate at point B. Using energy principles only, calculate the speed of the crate at point B. I'm giving you 3 minutes. You know you can do that. Using energy principles only, calculate the speed of the crate at point B. Let me know when you're done. I know this one is too easy. Using energy principles only, calculate the speed of the crate at point B. Yep. Well done. So you then say E mechanical at A is E mechanical at B, which is EP plus EK at A, which is equal to EP plus EK at B. And this is MGH Right. So this would be at A and this is going to be at B. The mass is 18 kilograms. The, the 9.8 gravitational acceleration, the height is 3. Obviously, the crate initially at rest, meaning therefore the initial velocity is 0. Then you have here, there's no height, so you have half. The mass is still 18 v squared. V squared. So that obviously at this point you multiply everything, and then v 2 by 18 by 9.8 by 3 square root. Right, so it is the square root. 2 by 18 by 9.8 by 3, which is I missed 18, should have also divided by 18 here. Obviously, the 18 cancels. So I was wondering why it was so large. So you're going to have the square root. Two by 18, 9.8, 3, 18, 7.67. 7.67 meters per second. That is the velocity. So yeah, Neo got it right. So well done there. Very well done. Very well done. You got that one right. So yeah, 7.67 is correct. Next question. Right, now at constant friction force, rather a constant friction force of 40.6 newtons acts on the crate as it moves. Remember that it lies down a frictionless slope from A to B. It's frictionless here. And then there's friction here. So a constant friction force of 40.6 newtons acts on the crate as it moves from point B up towards point C. The crate comes to rest at C, stops. Right, state the work energy theorem in words. State the work energy theorem in words. Right. The net. The net, work done. The net, work done. On an object. On an object is equal to the objects, or is equal to the change in the objects kinetic energy. Change in the object's kinetic energy. The net work done on an object is equal to the change in the object's kinetic energy. The net work done on an object is equal to the change in the object's kinetic energy. The net work done on an object is equal to the change in the object's kinetic energy. So that is the work energy theorem in words. It's going to be there tomorrow. They're going to ask you these things. Your Newton's, second law, those things are going to be there. Right, so now we've stated the work energy theorem in words. Using energy principles only, calculate the distance that the crate traveled from B to C. Using energy principles only, calculate the distance the crate traveled from B to C. Let me give you some 3 minutes there to try this question. Let me give you some 3 minutes to try this question. Let me give you some 3 minutes to try this question. Let me give you some 3 minutes to try this question. Right. Let us know when you're done, please. The distance Yep. Super fast. Good. 13.04. Super fast. Well done. Because normally when they ask the work energy theorem, then they're going to use it. So which means that at this point, we'll just say the net work done. So W net is change in kinetic energy. Because now, by the time it moves here, there's not going to be any applied force there, but the only force that's going to be there is going to be friction. Which means, therefore, you're going to have the net work done is going to be work done by friction. Okay, we continue like this. Which is F delta X cosine 180 degrees. Half M VF squared minus V initial squared. So, right, the frictional force, therefore, is 40.6. Right, so obviously 40.6 times delta X, but you know that the friction is in the opposite direction to the displacement delta X, making the angle 180 degrees. And the cosine of 180 degrees is minus 1. With half the mass, 18 kilograms. Right, and then we have the final velocity because it stopped. The initial velocity is what we got, which became 7 point that squared. And therefore, we're interested in finding delta X, which is 9 minus 7.67 squared divided by minus 40.6. Let's use a calculator to check this out. So then what we have here is that you have 9 times 7.67 squared divided by 40.6, which is 13.04. 13.04 meters, which means this delta x here is actually exactly 13.04 meters, and therefore it means that it's going to travel 13.04 meters from B to C until it stops. Okay, but yeah, there are many ways to do it. Let's look at 5.5. Right, the height of the track is now lowered. The height of the track is now lowered so that point A is at a vertical height of less than 3 meters. It was 3 meters before, but now it's lowered so that it is less than 3 meters. The same crate is again released from point A. How will the distance now traveled by crate A along the horizontal surface before it comes to rest compared to the distance calculated in question 5.4? Write only greater than, smaller than, or equal to. Explain your answer. What do we say here? What do we say here? Now we say, okay, this is now is not so steep. We reduce the height, so it starts at a smaller height. Right. We want to, how will the distance now traveled by the crate change? Will the crate travel far or will it travel less the distance? You see, that is the question. Will it travel further away or is it going to travel less the distance? But when we reduce the height of projection, sort of, the height from which this crate is released, what is going to happen? What is going to happen? What is going to happen? Obviously, because no. Okay, that's fine. I know we're trying. Because now it's going to be slower, because here it's going to be faster, because it's like from top. But now if the height is lower, then it's going to be smaller than. Never mind. It's going to be smaller than, because now if it's from the top, then it's too high. If a building is too high and then you throw something, it's gonna reach the ground with a greater velocity than when the building is too short. So it's gonna be smaller than. Why? Because the total mechanical or gravitational potential energy at A is less. Next, the velocity at B, yeah, the velocity or speed. The velocity or speed at B is less. Right. The velocity or speed at B is less. Okay, next question. We'll repeat again. Because now if you reduce the height, then it means that you're giving it a smaller speed. Okay, good. Yeah, you see, we're saying here now, here's the building. Here's a building, and Noah is standing on the rooftop. You throw an orange, or you release an orange. Just release it because you let the crate go. You release this orange and this orange goes down. If you are standing in the middle of here and you're standing on a balcony, which one will lead to the greatest speed at which the orange strikes the ground? Surely if you're too further up, then the orange, by the time the orange is going to be reaching the ground, it's going to be like too fast. And therefore, how will the distance now compare? Because if it is very slow, because now it's a smaller hill. It's a smaller hill. Right, it has less height. So it's gonna be less speed. Less speed, it means that it's not gonna travel a lot. It's just gonna travel and then stop. So it means that now want to compare how will the distance now be? So the distance is gonna be smaller than because the total mechanical energy, or what you call the gravitational potential energy at A, is less than the speed at B. Total mechanical energy at A is less. Velocity at B is less. That's it. The mechanical energy is less because the mechanical energy is the height. When the height is a lot, then the mechanical energy is a lot. Why? Because the mechanical energy at the point A is going to be just mgh subject to the height. Subject to the height. Subject to the height. So when the height is less, then it means that it's not so steep. The height is less, then there's less mechanical energy. Total mechanical energy at A is small, or it's less. Total mechanical energy at A is less. The velocity at B is what? Then if the mechanical energy is less, it means that at B it's not going to be too fast. It's going to be slow. 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 Okay, let's continue. If it's slow because of the less mechanical energy, then the distance is gonna be smaller than. The distance is gonna be smaller than. But if you start up high, then it's gonna travel a greater distance, yeah? Okay. Let's look at a stationary listener. A stationary listener records the frequency of the sound emitted by the siren of a police car. When the car is traveling at a constant velocity of 26 meters per second, approaches the listener, the recorded frequency is 615 hertz. The car passes the listener at time t1, then moves away from the listener. The recorded frequency now is 526 hertz. Ignore the effects of wind. State Doppler effect in words. Please pay attention to the statement of Doppler effect and make sure that you're able to remember it, because it's there tomorrow. They're going to ask you Doppler effect. Right. So it is the apparent change in frequency of the sound of the sound detected by a listener because the sound source and the listener have different have different velocities. Have different velocities relative to the medium. Relative to the medium of sound propagation. Relative to the medium of sound propagation. Relative to the medium of sound propagation. It is the apparent change in frequency of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. Relative to the medium of sound propagation. Relative to the medium of sound, it is the apparent change in frequency of the sound detected by a listener because the sound source and the listener have different velocities relative to the medium of sound propagation. This is called Doppler effect in words. Called Doppler effect in words. This is called Doppler effect in words. Let's look at 6.2. Use the information given to calculate the speed of sound in air. Use the information given to calculate the speed of sound in air. Let's give you some 3 minutes. Try this one. Please try this one. Use the information given to calculate the speed of sound in air. Use the information given to calculate the speed of sound in air. When you're done, please let us know. Right. When you're done, please let us know. 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 Right. When you're done, please let us know. Let us know. When you're done, please let us know. When you're done, please let us know. Right, when you're done, please let us know. Hello, my dear. Hello, my dear. Oh, right, right. We continue. Right, so let's continue. Let's continue. So now what you're going to have here would be, right? Well done. That's correct. Well done. So Nemo thought obtained 333.333 actually meters per second. And obviously this would be the velocity. So we'd have two instances. So we have an instance when we're moving towards the observer, using the information given to calculate the speed of sound in air. Moving towards, right? So here we're going to say moving towards observer. Moving towards observer. So now a stationary listener records the frequency of the sound emitted by the siren of a police car. When the car is traveling at a constant velocity of 26 meters per second, approaches the listener, recorded a frequency of this. Okay. When a car which is traveling at a constant velocity of 26 meters per second approaches a listener. So now moving towards the observer, the recorded frequency is 615 equals the velocity v. Okay, okay. So v minus 26. So the frequency of the source can be written as 615 v minus 26 over v, velocity. Moving away. moving away from observer. Which is VL divided by VS. The car passes the listener at time t1, then moves away from the observer. The recorded frequency when it moves away is 526. But again, if it moves away, okay, if it moves towards, then it's negative. But it moves away, then it becomes a plus. It becomes, if it moves away, then it becomes a plus. Towards is negative, away becomes a plus. Then you have the frequency of the source. At this point, the frequency of the source becomes 526 V plus 26 divided by V, which is 615 V minus 26 V, which is 526 V plus 26 V. Okay, so the V cancels, giving us 615 divided by 526 V minus 26 equals V plus 26. You multiply through, which is exactly 615 divided by 526 V. Then we have this. Then we minus V, which is 26 plus 615 divided by 526 times 26. Factor out the V, then you have 615 divided by 526 minus 126 plus 615 divided by 52626. V is 26 plus 615 divided by 52626 divided by 615, 526 minus 1, and then you get the answer. So now, so you'd have 26 plus 615, 526 times 26. Six one five 526 minus 1, which is 3333 point that 0.33. Yes, 333.33 meters per second. So this is going to be exactly the velocity of the sound in air. Let's look at the next question. Calculate the wavelength of the sound emitted by the police siren. Calculate the wavelength. Calculate the wavelength of the sound emitted by the police siren. What is the formula for wavelength? Right, the formula for wavelength is that speed is equal to speed or velocity is equal to frequency times the wavelength. Right. It's exactly this. But obviously now I want the wavelength of the sound emitted by the police siren. So we already know that if in the beginning, this one, we know that Fs is 615 V minus 26 over V. The frequency of the source is 615 V minus 26 over V, which is 615. Yeah. Dividing everything, dividing every single bit of thing, right, using a calculator here. Would be the same as 615 times 123.33 minus 26 close. 123 which is 567.03. 567.03 hertz, which means V is F lambda 333.33. So that then the frequency, the frequency of the source is 567.03 because we need the wavelength of the sound emitted by, so it's the frequency of the source, but you need that wavelength, which is lambda. Obviously, then we have the lambda, which is the wavelength, 333.33. We divide by 567.03, which means the wavelength is what? The wavelength is what? 123.33. 567.03, which is 0.59. 0.59 meters. 0.59 meters. 0.59 meters. So calculate the wavelength of the sound emitted by the police siren. Calculate the wavelength of the sound emitted by it is 0.59. Okay, let's look at the next question. Sketch the graph. Ignore the effects of wind. Sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away from the listener. Label time t1 on the graph. No values need to be indicated on the frequency axis. Sketch the graph. Yeah. Okay. You want to write which one? You want to write this one? Okay. The wavelength of the sound emitted by the police siren? Okay, that's fine. Let me give you a chance. Because these questions are going to be there tomorrow. They're going to ask you the wavelength tomorrow. So you need to remember that wavelength, to calculate wavelength is actually V equals speed equals frequency times the wavelength. But obviously there are at least two frequencies. I mean, it is the frequency of the source and the frequency associated with the listener, detected by the listener. So those are the kinds of things that you need to take note of. So the kinds of things you need to take note of. Right, right. Okay. Okay, good. Let's move to the next question. Okay, now here's an interesting question where we need to sketch the graph. Sketch a graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and then moved away. How will the frequency versus time change from the moment it was moving towards the listener, past the listener, and then moved away from the listener? How will the frequency versus time graph be? How will the frequency versus time graph be? How will the frequency versus time of the graph be? Right, so in 6.4, this is what you're going to have. So we're going to draw the frequency time. Now we're going to have the frequency. Okay, in the beginning, sketch a graph of recorded frequency versus time for the motion of the car as it moves towards the listener. Moves towards the listener. Right, so the as it moves towards the listener, then the frequency is some value. It passes the listener. By the time it passes the listener, before it moves away from the listener, there's a drop. And then it actually moves away from the listener. So this would be the frequency in hertz versus time. Because when it moves towards the listener, the frequency is some constant, and it passes the listener, there's a drop. It moves away from the listener, then there's a drop again. So this, no values are needed there. But this one is going to be time one. Going to be time one. Okay, they're going to ask you tomorrow to sketch a graph of recorded frequency versus time for the motion. Okay, this paper is going to it's pretty much tomorrow's paper. So just taking note of exactly the way we're doing things here. So label the term T1 on the graph. No values needed to be indicated in the graph. So by the time then it approaches yeah, towards the listener, it's constant. It passes the listener. By the time it passes, then the frequency decreases. It moves away, then the frequency is much smaller. Then the frequency is much smaller. Let's look at the next question. I hope you have written this one because it's going to be there tomorrow. I'm speaking to you if I'm joking. I'm telling you the truth. This is the paper. This is the paper. Okay, yeah, let's try the next one. Yeah. Okay, good. Right, so now, okay, x. X is the point. 0.025 meters away from the 4 nanocoulomb point charge. See the diagram below. Draw the electric field pattern due to the plus 4 nanocoulomb charge. Okay. You're thinking about that one? Right. Draw the electric field pattern due to this one. Obviously, due to that, what you can see, it's positive, so outside, outward, outward, outward. So draw the electric field pattern due to this one is outward, yeah? Calculate the magnitude of the electric field at point X. Okay, so the magnitude of the electric field at point X is going to be K is 9 times 10 to the 9. The charge, which is 0.025. Nine times 10 to the ninth power times 4 times 10 to the minus 9 divided by 0.025 squared, which is 5.76 times 10 to the fourth power. 5.76 times 10 to the fourth power newtons per coulomb. And this is the magnitude of the electric field at that point. Is the magnitude of the electric field at that point. Is the magnitude of the electric field that point, yeah, because at this point, then we want to find the magnitude of the electric field. We use E equals KQ over R squared. But obviously this one is for the uh, the plus 4 nanocoulomb charge. But you note that the nanocoulomb is 4 times 10 to the minus 9 coulombs for the nano. For the nano. Okay, we're gonna take a break, I think, at some point. When we finish this question. Because we've done a lot already. We've done a lot already. Okay, done copying. Move on. There are so many. That is why I'm just thinking there are so many. Let me see. Okay, there are two. There are two. There are two, but just that is a story. Okay, there are two. Well, we're done with this question 7. Two identical neutral polystyrene balls, A and B, are suspended from a ceiling by insulated light inaccessible strings of equal length. Okay, yeah, we're going to take a break of equal length as shown in the diagram. Okay, you have these polystyrene balls A and B, and this is inextensible strings, and they're hanging like that. Ball B is then given an initial charge there. Ball B is then given an initial charge QB of unknown magnitude. Yeah. The balls attract each other, touch, and then repel each other. Okay, the balls come to rest with their centers 10 centimeters apart so that each string makes an angle of 9 degrees. Okay. Ball B is then given an initial charge of unknown magnitude. The balls attract each other, touch, and then repel each other. Okay. So B was injected with some negative charge, and then suddenly these attract each other, and then suddenly they start repelling each other. Right. The balls come to rest with your centers 10 centimeters apart so that each string makes an angle of 90 degrees with the vertical, rather 9 degrees with the vertical. See the diagrams below. State Coulomb's law in words. State Coulomb's law in what? In words. State Coulomb's law in words. Let us state the law. To state Coulomb's law in words, we say the magnitude. The magnitude of the electrostatic. Magnitude of the electrostatic force exerted by 1 point charge on another is directly proportional to the product of the magnitudes of the charges, and inversely. Inversely proportional to the square of the distance. This one is there tomorrow. Of the distance between their centers or between them. The magnitude of the electrostatic force exerted by 1 point charge on another is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. Right, so this is what we call Coulomb's law in words. It's going to be there tomorrow. Right. And then now we need to just have this more calculation to do. Calculate the magnitude of the initial charge QB given to ball B if the mass of each ball was 0,012 kilograms. Calculate the magnitude of the initial charge. Calculate the magnitude of the initial charge. All right, calculate the magnitude of the initial charge. Okay, so obviously take note of Coulomb's law. I know you're very exhausted now. I don't want you to be too tired because now you need to revise your own things. I gave this a bit of time, obviously, to relax from yesterday, to revise, but I know you would, revision never ends. Revision never ends. Right. Okay. All right. You're saying, can we do dynamics? Okay, we shall spend time on dynamics as well. We'll spend time on dynamics. Right. So now I want us to quickly finish off with this question and calculation, because you see, the moment that this is actually in this particular direction, or this is suspended there, and want to calculate the initial charge. Now, what is happening here is you're going to have this tension, electrostatic, the weight. So, right, so you're going to have the weight straight down. This is exactly 9 degrees. Fe, the weight. Then now we're going to do 10 theta. Right, if you do 10 theta, for example, this is exactly 9 degrees. I mean, that's what we're saying here. It's exactly 9 degrees. So that at this point, then you have the 9, not 90, but 9 degrees. So that then if you're going to do the 10 of theta, it's going to be exactly what? Opposite of adjacent, so you can do the 10 of the tangent of 9 degrees. Which is opposite of adjacent. And then we'd be interested in finding the electrostatic force for 9 degrees. Which is mg to 9. Which is the mass is 0 0.0, comma 0.012 times 9.8 times the 10 of 9 degrees. You multiply. times the tangent of 9 degrees. Okay, then we're getting 0.0186. 0.0186 newtons. That is the electrostatic force that we've got. Right, if this then is the electrostatic force that we've got, then we would take the electrostatic force and analyze it as follows, and then say the F electrostatic, which is Q1 QB divided by R squared. 0.0186. 9 times 10 to the 9th power. Okay, obviously, the electrostatic force we've already got. Calculate the magnitude of the initial charge to be given to this before of the mass of each ball was this. Zero comma 1 squared. Yup. Which is 0.1 squared divided by 9 times 10 to the 9th power. 0.0186 divided by 9 times 10 to the 9th. Then when I do the square root, so this is 0.0186 times 0.1 squared. You divide by 9 times 10 to the 9th power. Which is 1.44. 1.44. So you're getting the charge to be 1.44 times 10 to the minus 7 coulombs. Which means QB is 2 times 1.44 times 10 to the minus 7 coulombs. So you multiply these things, and then you multiply this by 2. Because it was shared, this became the charge immediately when these were a distance, when they were apart. But before then, B had all the charge, it was double the charge that was shared. So this was the charge on each, but before that, it became double, which is 2.88 times 10 to the minus 7 coulombs. 2.88 times 10 to the minus 7 coulombs. Right, that's the answer. That is exactly the answer. That becomes exactly the answer. Right, you wanted us to do some dynamics, because this is the last question. And then yesterday we looked at, was it whenever we did this paper, because we took a break, obviously, for some days. I think we're not discussing. And we had to finish the electricity question, but we did not get to finish it. You wanted us to do another section. What section would you like us to do? We take a break or we continue? Dynamics. Okay, let us look at dynamics. Let us look at dynamics. You mean question 9? You mean question 9? Or you mean question 10 on photoelectric effects? Okay, good. Let's look at question 9. Right, question 9. This question must be started on a new page as usual. The simplified diagram below represents an AC generator with a coil rotating clockwise. X and Y are 2 points in the external circuit. The simplified diagram below represents an AC generator with a coil rotating clockwise. Okay, the coil is rotating clockwise. X and Y are 2 points in the external circuit. Okay. What is the direction of the current in the external circuit? Right X to Y or Y to X? Right, a couple of things obviously that we're seeing that obviously this coil is rotating clockwise. So X and Y are 2 points in the external circuit. So when it's rotating clockwise, we're able to see that the current, obviously, because this is the north end, that is obviously the south pole. Therefore, we have that the direction of the feed lines will be from the north to the south pole. And therefore, as a consequence, then the current will run from Y to X. So the current will proceed this way. So we'll run from Y to X. So the correct answer is Y to X. The correct answer is Y to X because the north and the south, this is actually running clockwise. And when it actually runs clockwise, therefore the current is Y to X. Well done. State the conservation of the energy conversion that takes place in this generator. All right, so obviously in this case, we can see that there is mechanical. The energy conversion is mechanical, or kinetic energy, or kinetic to electrical energy. Kinetic to electrical energy. Kinetic to electrical energy. Mechanical to electrical energy. Because now we're just having the moving parts. The moving parts are, mechanical, and therefore it's producing electrical energy. Let's look at 9.2. Mechanical to kinetic energy. 9.3. The maximum voltage produced by the generator is 125 volts. This is the maximum voltage. That is Vmax. Right. Vmax is 125 volts. Define the term root mean square voltage. Define the term root mean square voltage. Right. Root mean square voltage actually means we then say the RMS. The RMS potential. Okay. Okay, you think we'll do that last. Okay. The RMS potential. The RMS potential difference is the alternating is the alternating current potential difference which dissipates the amount. Okay, obviously here we're saying which dissipates or which produces the same amount of energy as an equivalent direct current DC potential difference. Potential difference. Potential difference. Okay, the RMS potential difference is the alternating current potential difference which dissipates or produces the same amount of energy as an equivalent DC potential difference. So the RMS potential difference is the alternating current potential difference which dissipates or produces the same amount of energy as an equivalent DC potential difference. We repeat, because they're going to ask you this one tomorrow. So the way to learn this is to repeat until you don't forget, like a song, when you're singing a song. The RMS potential difference is the alternating current potential difference which dissipates or produces the same amount of energy as an equivalent DC potential difference. Right, so now calculate the root mean square voltage. So obviously this one would be very easy, and you then say the V RMS. The root mean square potential difference. V max divided by the square root of 2. 125 divided by the square root of 2. Which is 125 divided by the square root of 2. And then you're getting 88. Which is 88.39. 88.39 volts. So now, obviously here we need to get the VRMS. So we're able to see, therefore, that the VRMS, it's Vmax divided by the square root of 2. We already have Vmax because we have been told that the maximum voltage produced by generator is this one. So the maximum voltage is that one, and it's divided by square root of 2. It is 88.39. Okay, let's look at 9.5. You're writing. Yeah, I'm just moving. Just moving. Right. Okay, good. Let's look at the next one. Okay, good. Let's look at the next one. Now, here, the officers have been told that the maximum voltage, which means that Vmax, Vmax is 125 volts. Okay, now the total resistance in the external circuit is 42.4 ohms. Calculate the maximum current induced. Yep, what's the answer? So at this point, obviously, we know that the total resistance in the external circuit is that one. The total resistance in the external circuit is 42.4. And then now if we have I max divided by R, I max, which is 125, divided by because it is the I max, I is V over R, Ohm's law. So that I max is V max over R, but V max is already 125. The R is 42.4. And therefore, which means that I max, calculate the maximum current induced. Calculate the maximum current induced, which is 125 divided by 42.4, which is 2.95. 2.95 amperes. 2.95. So if you need to calculate the maximum current induced, I max, but I max is V max over R. But you're seeing that VRMS is V max divided by the square root of 2. This is like the formula you need to learn for VRMS. This is V max divided by that. But the I max is V max over R. Okay, so yeah, let me see what you're thinking. All right, good. So you remember the formulas. What are the formulas? If they say tomorrow, because they're going to ask you tomorrow to calculate the maximum current induced. So, which means that I max is V max over R, but VRMS is V max over the square root of 2. Let's look at the next question. Let's look at the next question. Yeah. Okay, good. We can take a break, right? Good. We can take a break. I think that we've done something and then we can take a break. Okay, but there's a question that's going to come tomorrow. This one. Yeah, there's a question that's going to come tomorrow. 9.6. Let's just do 9.6. This one. The maximum voltage produced is 125 volts. The generator induced current at a frequency of 20 hertz. The coil started rotating from the initial position. Okay, so the coil started rotating from the initial position as shown in the diagram above. Sketch a graph of induced current versus time for 2 complete rotations of the coil. It's going to be there tomorrow. Indicate the following on the graph: the time taken for 2 rotations, the maximum current induced by the generator. Okay. So now let's just do this one. Then what you're going to have here, we've already dealt with these, but now obviously if we need to indicate, sketch the induced current versus time. So you're going to need current, time, time in seconds, 2.95. Then it, okay, because we got to the 2.95, which was Imax. The Imax was 2.95 amperes. So we're going to put it there on the graph. Then obviously, but we need to sketch the graph of induced current versus time for 2 complete rotations. Right, Imax was put there. Then here we're going to have minus 2.95. Then it goes further up. Right, and then it goes like this. So now we're going to seal it here. And then we're going to seal it here like this. This one is 0.1. You see, what we're then seeing here, this is we have to sketch a graph of induced current versus time for 2 complete rotations. 2 complete rotations. Meaning, obviously, you have here a rotation, and then it repeats again. But it's said already, the coil started rotating from the initial position. From the initial position. And from the initial position, obviously, it actually indicates that obviously we will have to start sketching it at the Imax, and we're to sketch a graph of induced current versus time. Induced current versus time. And that is the graph for 2 complete rotations. Okay, it's not the only way to sketch the graph, but you can do the opposite as well. You can do this. You can start like this. So you can take the opposite. So that this is minus 2.95, 2.95 time the current in amperes. Right, I must thank you for joining us. I think that we need to take a break. Then we'll see what we can do. Right. We'll see what you can do. We'll see what you can do. All right. All right, we'll see what we can do. All right, we keep in touch. Okay, yeah, we'll keep in touch. We'll talk on WhatsApp and see maybe we can still do something before tomorrow. I don't know. We'll see. Okay, but yeah, but thanks for now. Now we'll take a break, drink water. I don't know, do something, revise your stuff, revise. Right, revise something, and then we'll talk. Thanks, Noah. Goodbye for now. I'm gonna send this recording in the next couple of minutes. Yeah. Thanks, Noah. Goodbye for now.